Hello, my name is Rebecca and I'm a PhD student at the University of Queensland. Today I'm presenting my research on the formation of the smallest galaxies. Large compact dwarf galaxies, or UCDs, are intermediate objects between globular clusters and dwarf galaxies. It is believed that UCDs are either massive globular clusters, the high mass end of the globular cluster mass spectrum, or in particularly massive galaxies, or that they are the strip nuclei of dwarf galaxies that were disrupted through interactions with other, more massive galaxies. In this study, we used the hydrodynamic Eagle simulations to test if UCDs formed by the tidal stripping model in massive Virgo-like clusters. To identify galaxies which may be stripped, we searched the merger trees of galaxies and clusters. We modify the simulations by defining the central most found particle of nucleated galaxies as the nucleus and tracking it through the simulation. The reach of zero positions of these most found particles are then determined and their properties are derived. In our first published paper, we determined the numbers, masses, and distributions of our sample of simulation nuclei and compared them to observations of UCDs in the Virgo cluster. Figure 3 shows that the number of massive UCDs found in Virgo is consistent with the number of massive strip nuclei we predicted to contain. Figure 4 shows that the radial distribution of strip nuclei around a massive simulated galaxy is consistent with the radial distribution of UCDs around M87, a massive galaxy in the Virgo cluster. Therefore, our results show that strip nuclei can explain the numbers and radial distributions of UCDs in Virgo. In our second paper, we determined the internal properties of our sample of simulated strip nuclei and compared them to observations of UCD properties. Figure 5 shows that the simulation predicts strip nuclei colours are consistent with the colours of observed UCDs in Virgo. One consequence of UCDs being strip nuclei is that they are likely to retain the central supermassive black holes found in galaxy nuclei. Figure 6 plots the supermassive black hole masses of simulated strip nuclei against their total masses and compares them with the studied supermassive black holes in observed UCDs. We find that the simulations accurately predict the expected masses of supermassive black holes in UCDs, a strong test of the simulations that establishes that they are predicting accurate results. In Figure 7, we compare the number of galaxies that will have been disrupted to form strip nuclei with surviving galaxies in a simulated cluster. We find that the expected number of supermassive black holes in strip nuclei depends on the occupation fraction of black holes in low-mass galaxies. Assuming pessimistic occupation fractions, strip nuclei represent a minimum increase in supermassive black holes in galaxy clusters of 30%. In conclusion, our new model of UCD formation shows that the tidal stripping of galaxy nuclei can form the observed UCD populations. High-mass strip nuclei have consistent numbers, distributions, and colours with UCDs in Virgo. The simulation reproduces the expected supermassive black hole masses of observed UCDs, and we find that strip nuclei contribute a large number of supermassive black holes in galaxy clusters. Therefore, there is a high probability that UCDs form from the disruption of dwarf galaxies. Thank you.